So today we will finish up our cohomology discussion, as well as give a brief introduction to stability, discussing how stable our results are in terms of the persistent diagrams. If you distort the data a little bit, do you expect the persistent diagram to change? But first, a reminder that next week will be the workshop on modern applications of homology and cohomology. So we will not have a regular class next week, but you are welcome to listen to any of these talks. Some of these talks may be a bit more advanced than the last workshop talks. So I will also send an email on Sunday with a list of recommended talks from the past workshop, as well as some seminars that have been recorded outside of the workshops at the IMA. So you'll get that email this Sunday. Also, if you have questions during the live video streaming, you can ask them directly within the live video streaming. But if you have questions outside of that, you're welcome to email them, and I will pass on your question to any of the participants at the workshop. If you are attending, I will again organize a group lunch. If there's someone in particular you would like to have lunch with, let me know. I will probably do the group lunch on Tuesday, but if you have a preferred day, again, let me know. Any questions about next week? So again, next week, no classes, except for I do highly recommend listening to some of the videos that I will email on Sunday, as well as many of these as you have the time and background for. So just to recall again, our goal is to find a function from our data set into the circle so that we can sort of do a dimensionality reduction while still preserving sort of the structure of the data. Thus, we would like a nice map, and if we can get a nice persistent cocycle, then we can use that cocycle to come up with that map, and that's what we will discuss today. If we do have a cycle which is not persistent, so we can see that this cycle will, go away. You can see that this cycle, which is cocycle, which is not very persistent, most of the points get mapped over here. That's not a very good structure-preserving map from our data to the circle. So we want to go ahead and work with the persistent ones. Now, in order to simplify things, I gave very basic descriptions of cohomology. I really didn't mention, I mentioned that there was duality, but I didn't discuss it at all, and that is a very basic concept in cohomology. So if you want to see more about cohomology and the duality, both in terms of the basic definition as well as some duality theorems, I recommend seeing Chapter 5 in Edelsbrunner and Harar's book on computational topology. You can also see standard textbooks in algebraic topology. They will also give you the basics too, of course, but this one was written by applied people, so you might like that as a first introduction. Also, we mentioned that one can get the same information from the barcode for both persistent homology and cohomology. If you would like to see the map between the two, I recommend De Silva, Morozova's, and Johansson's paper in Inverse Problems in 2011, and they will give you the map between the two barcodes and show that they basically have the same information. However, the reason that we are interested in cohomology instead of homology, even though the barcodes might give us the same information, what we want are the maps. So if we can get the map that goes from our simplicial complex, including our data points, into the integers, then we can get this continuous function into S1. Oh, but with our proposition 1, we didn't really like that because it sent every vertex to 0. But by understanding this map, by being able to create this map, we were then able to discuss Proposition 2, or at least start discussing Proposition 2, where we now have a much superior map, one that is actually useful. It still goes from our simplicial complex into the circle, which is what we want, but now it will send an edge AB linearly onto an edge, onto an interval of length alpha bar of AB, so going around multiple times. On Wednesday, I seemed to flub a few words and things, and I think I said it was just going to a number for this one. But just like for Proposition 1, when we're sending an edge, it is wrapping to an interval around the circle, possibly multiple times around the circle, depending, it could be in the positive direction or in the negative direction. What we meant by linearly is, in reality, as we started to discuss last time, we can really think about this as a map first into the real line, but we might have this edge AB where maybe A goes to, say, 0 or some other number. B might go to, for example, pi, and then we would want to map our edge AB linearly onto this interval. But now we can mod out by the integers, which means this might go to the interval 0, 1, this might go to 1, 2, this might go to the interval 2, 3. Linearly, all of these should be of equal length, let's pretend, and this one is the remainder once you divide it through by z. And so we can map this thing once, twice, 3 times, and a little bit more. And so we would be then projecting to our circle once, twice, 3 times, and a little bit more. And so this entire interval would be mapped to wrapping a little bit more than 3 times around S1. So this would go once around the circle, twice, 3 times around the circle, and then a little bit more. And that's what our map would do on our interval AB. Any questions about that? So if we now want to map our entire simplex into AB, maybe into S1. So maybe this is our edge AB, and maybe we will go ahead and in R send this thing from 0 to pi, and then maybe from B to C, maybe, so we've got from 0 to pi, and then maybe from B to C, I'll go from pi to, say, 1.2. And so we'll map this thing here to this interval right there. So going in the other direction. And then we can map C to A, going from 1.2 to 0. And so what we've now just done is we've taken this cycle and we've started off at 0. We then mapped to once, twice, 3 times, a little bit more to pi. That was our edge AB. Then for our edge BC, we start off at this point, go back until we have gone to 1.2. So we go back, we've got 3, wrap around 2, a little bit more until we get now to 1.2, and then go back again until we've gone 1 full around and a little bit more to back to 0. And so now when we add these things up, the entire cycle started at 0 and ended at 0. We didn't have to start at 0. I could have started at 0.5 or, pi over 3, wherever I want to start. But the main thing is whatever our starting point is for our cycle, then after we've, done a few wrapping, we then wrap, around a few, we can go multiple directions. but eventually we end up for our cycles back to the starting point. If we have done that, then we can extend, just like we did last time, to our entire face. And so we can extend the map to the entire simplicial complex into S1. And so now we have the map that we want. It's just now not everything is going to be mapped to 0 anymore, so not all our data points will get mapped to the same point. We will now have a much more interesting example of a map on our data points. So this is the map that we would like to create. And as long as we know where our vertices go, we will be able to fill out the rest, as long as the cycles go to someplace where wherever our starting point is, our ending point will go to exactly the same place. And we will see that within our next. So we'll now take a look at the proof of our proposition 2. So this is just a rewording of proposition 2. So what we are given, if we go back to read our proposition 2, what we were given was this cocycle, functions from our simplicial complex into the real numbers. We also had a function from our simplicial complex into the integers, as well as actually it was our one chains into the integers, our one chains into the real numbers, and now our vertices into the real numbers here, such that our alpha bar is going to be the sum of these two one chains right here, which had better be cocycles since this thing is also cocycle. So if we have all of these things right here, if we have alpha bar, alpha, and F, then our goal is to create this map from our simplicial complex into basically S1, our real numbers mod Z. So into our circle, such that this thing here goes to interval of our length, alpha bar V1 VK. And so alpha bar V1 VK goes from our map, sends our edges into real numbers. And so it's going to send our edge, so our alpha bar, remember, sends all our edges into real numbers. And so if I've got an edge V1 VK, if I take this edge right here, it will go to this real number, and that is our thing, and we want it to be this theta to have that interval go through that length. So the question is, how do we define this function? So we just want to create this, and the nice thing about this proof is it will be constructed. We will actually know what our theta is. This won't just be an existence proof. We will actually create theta. So any questions up through here? Okay. So in our theta, well, we're going to start creating it on our vertices. We want to know how should we define theta on a vertex. So how should we define theta on a vertex? Well, we want to have it go to this particular length right here. This just goes to the integers right here if we just say what it, we're projecting onto R mod Z. So as long as we know in terms of our circle, if we send it to some place on our circle where the difference between these 2 points is basically where these things come from, then we can go around our circle as many times, so our mod Z component won't matter. We just need to go a little bit more in terms of here. And so what we can do, there is an actual obvious choice. The obvious choice is to let our theta VI equal to F of VI mod Z. And that way, if we let our theta VI equal to F of VI mod Z, then however many times I go around, I can do that just fine. I can go around the circle as many times as I want to, but I will get to my right starting point or my right ending point when I take a look at this interval. Let's show that we do get to our right starting and end point. If I do subtract all of these, both of these things here, well, I get f of vi minus f of vk. So I'm taking vi and vk. So when I subtract off that, I will be getting this, mod r integers again. But if you remember our boundary map, how is our boundary map defined? How is our boundary map? I need to lift this thing to what my edges do, and so I'm interested in d naught of f. Well, this is how I would define d naught of f applied to my edge vi, vk. So in better handwriting, we can see that what we're getting is if we, so all of this is mod z, but if I send theta vi minus theta vj to f of vi minus f of vk mod z, well then that is by definition, f of vi minus f of vk is by definition equal to this thing right here. Well, this, if I subtract off minus alpha from both sides, I get my d naught of f is equal to alpha bar minus alpha. So I get alpha bar minus alpha applied to my edge. But this thing right here, its codomain is the integer, so this thing right here is an integer. So if I'm working mod z, all my integer terms go away, and so I just get alpha bar of vi vk. Thus, I can now define my map if I do have that say my theta of vi goes to, maybe we'll have theta of vi go to, say, an angle of pi over 2, so maybe this is pi over 2, and then maybe we'll want theta of v2 went to this number over here. Then we can now go ahead and define our map on theta of vi vk. So we can now extend our map. So we've defined our map first. So our step one is to define our map on vertices. We can now define it on edges. To define it on edge, I will just define it to be the interval that goes around as many, integer times as I want. So I'll start here, go around as many integer times as I want, and then go around a little bit more, and it will now agree with my map on the vertices. So what I'm doing here is I first define my map on all the vertices. Since these things are all disjoint, we have a nice continuous function. I then want to define the map on all my edges. Well, my edges are disjoint except for where two edges intersect in a vertex. So I can send my edge wherever I want as long as it agrees to where my vertices go to. I want it to be of this length, and it can be this length. I just say that whatever, if this length is 3.2 or 5.7, it's 5.7, I'll go around 5 times and then go around the 0.7. And since it agreed with this difference right here in terms of the length, it's going to agree to where our vertices ended up. And so now we have a map that sends our 1 simplices and our 0 simplices to places that make sense. So we now have a nice continuous map for both our vertices and our edges. Any questions up to this stage? We then need to define it on our entire simplices. So now we want to define it on our faces, our tetrahedron, etc. But because we have cocycles, the same idea worked in terms of proposition 1. So we don't actually need proposition 1, we just need the idea between the proof of proposition 1. If I have a cycle that starts off at pi over 2, wraps E1 around 5.7 times, wraps E2 around maybe 1.5 times, and then maps E3 around to the negative of the sum of those two. So I now get back to pi over 2 with this winding number 0. Then I can do the same trick of, instead of going all the way around whenever I was turning around, I'll now map this thing around to, oh, let's not go the full way around. We'll go a little bit less, a little bit less. And since our entire thing is homologous to going around 0 times, winding number 0, for the entire cycle, we can now extend this thing. We can now extend this thing to any higher dimensional simplices in a manner similar to what we did for proposition 1. Any questions about that? Okay. So we now have this map that we want from our simplices into S1. So now that we have this map, let's take a look at what this map, how we can use it in particular applications. So in this cocycle paper, the authors looked at a variety of different maps. If we take an arbitrary cocycle, say we take a look at this cocycle here for something that is not very persistent, whether it's this data point or this data point or that data point, something that is not very persistent, well, we don't like this map because, as we said before, it doesn't represent the structure of the data. All these points get crushed to something like this. So instead, we want to choose something that is nice and persistent. And so we will, in the algorithm, choose something that's nice and persistent to get nice maps. There's a little bit more to it. After we look at some of the example files, we'll actually look at a summary of the actual algorithm. But let's take a look at, so the basic idea is to find a nice persistent cocycle and then use that to come up with this theta map that will then map the simplicial complex, which we can then restrict to our data points. So we had this data that actually took our x, but then we restricted it to our data points onto our circle. Let's take a look at what this kind of thing looks like. We can take a look at the map of how many points go to where in our data set. So if this is our map of S1, so S1 can be thought of the unit interval from 0 to 1, or if you, so from 0 to 1, we can just map it, around here. And so this is our 0 to 1, where we then glue these 2 points together. So if I glue 0 and 1 together to here, so we've got 0, gluing it to 1, we get our circle. This map says the number of points, basically. So this is the number of points that basically get mapped to here. And you can kind of see that in terms of our color coding, the number of points that get mapped to our various different things. So that is our function here, where we take a look at this axis is our S1, and then this is the number of points in our data set that get mapped to a particular point in S1. And you can see it's nice and evenly distributed. If I were to take a look at this next one down here, if I take a non-persistent cocycle and use that to create my theta map into S1, well, look at this. We have a whole bunch of points that get mapped to the same point. So when we project this thing to S1, so when we project it to the circle, a whole bunch of points get mapped to the same point. And thus, we can see that this one here that mapped up to S1 is going to be a lot, it preserves, it's not perfect, it's not, this one-to-one correspondence that sends, every point, nicely to a circle. It's not quite one-to-one, but it is a lot better than this thing here that sends all of these data points to a single point down here. So we like this map. This map, you can see, preserves the structure of the data points much better. So any questions basically with respect to this graph and here versus these two, taking a persistent cocycle versus a non-persistent cocycle. Okay. So let's go back up and take a look now at our other graph right here. In this graph, what we're doing is taking a look at S1 versus your data. So this is basically a scatter plot of here, a point here tells me of, here I've got, if I take a look at, it actually might be data versus S1. They didn't say which axis corresponded to which. So let me change this for data to S1. It might be either way. But if it's data versus X1, I've got my data point versus where it gets mapped to on S1, so where it gets mapped to on S1. So we can take a look at the scatter plot of X versus where it gets mapped onto theta 1. And we would expect in this particular example here with my nice fake map, this is a fake map, you can see that 0 goes to 0, pi over 2 gets mapped to pi over 2, etc. I should get a nice diagonal here. I should be getting a nice diagonal. We don't get quite a diagonal, and that's because my maps are fake. They didn't actually show the actual map, but you can see that there's just a slight rotation. And so instead of sending this, if I put my theta and say this is my angle 0, this right here is my angle pi over 2, we can see that points along 0 get mapped to, point somewhere around here. Points that are pi over 2 get mapped somewhere around here. And so there is this thing where we've done a slight rotation off of here. So I faked the map before. I thought for pedagogical purposes, it would be nice to see something where it was just a direct, this point went straight to here, there. Here, this is actually also faked as well. Again, they didn't have this actual picture in their paper, so I made it up. But we can see from the data that we are going from circle to circle, but what we don't expect when we're doing a cocycle, we haven't fixed what our 0 point is over here. We haven't fixed our 0 point, we didn't fix, the cocycle map does not fix our 0 point going to 0. You could do that if you wanted. If you wanted to, you could, just subtract off whatever this angle here is. So you could subtract off that angle. Let me use a different thing since we've already used theta for our map here. We could subtract off this angle here. But there's no real reason to do that. We can see that since remember, this point over here on our circle, so if this is our S1, well, we didn't draw S1 as a circle. We drew S1 as the interval from 0 to 1, where we then glued 0 to 1. So this is our notation for saying we glued 0 to 1. So if this point is equivalent to this point, that means this point is equivalent to this point. And so we really do get a diagonal. It's just shifted by this value here. So if you get any kind of correlation plot where you see this kind of thing, then you do know that you are really seeing our circle again. So if we do this plot where we've got x versus theta of x, and you see that it's basically these things where if I move this thing down here, it's just we've moved our diagonal. We've just done a translation of our diagonal. We really are recovering the circle very well. Any questions about that? One thing that I forgot to mention, which is also actually quite important, whenever you come up with a new algorithm, so this is a new method for creating these functions theta, it is good to check it on artificial data. So they created this artificial data of, all these data points, that they knew lied on an S1. So all of these experiments that they're doing is on data that has been artificially created, where they know what they want. They know that this thing is an S1, where they basically just added a bit of noise to their data. So they generated points on S1 and then created noise. And then they check to see, do you get your circle? Can you see your circle? And sure enough, when you see this scatter plot, it correlates perfectly with S1. And so we do see that we recover S1 with this map theta. Any questions on that? Suppose we now compare it to where we've now taken a cocycle that is not very persistent. So if I increase my epsilon balls, this circle will not last anywhere near as long as this circle. And now what happens if we plot x versus theta of x? Well, if I plot my data points versus where it gets sent to, so this getting sent to, so I've got my x versus theta of x, almost all of the points go someplace, I guess it looks like it actually goes someplace in the middle right here. Looks like it goes pretty much somewhere around there. They almost all go to the same point. So if I take an arbitrary data point, they almost all go to the same point in S1, where my S1 is represented going from 0 to 1. Except for around here, then we can see that we do have some points that now go to various different other points along S1. So we can see that these points here do get mapped to a variety of other points on S1, but it's in a very small interval. It's in a very small region. And so we can see that this does not correlate very well with S1, and so this does not preserve our structure very well. Versus this one, we can see preserves this structure very, very nicely. Any questions on that? We can also take a look at more interesting examples. So in this case, they embedded S1 as a trefoil knot. So they embedded this as a trefoil knot. If we take a look at the persistent cocycle, then they get something that's, again, very similar to a circle. Again, there's an offshoot, but this point is equivalent to this point. So we are mapping to the circle, but you'll notice that there is this, something like this. Well, they drew the trefoil knot, the map that they used, they drew the trefoil knot specifically on the torus. So if we start drawing this thing on the torus, so let's draw this on the torus right here. So that might be the same knot, hopefully. If we have the same density of points, so if I have the same density of points along this outside as I do on the inside right here, so if I have the same density of points here as I do here, let me rephrase that. Suppose I have the same number of points along this longitude as I do along this longitude. So if I have the same number of points along this longitude as well as along this longitude, well, that will increase the density locally here because we now have, this longitude is much smaller than this longitude. And so frequently when you're creating points living in R3, depending upon how you create these points, you will not necessarily get the same density of points in this region as you would in this region. And so they did the same density along the longitudes in terms of the embeddings, and you can see that in this sort of shape here. But still, it does reconstruct our map very well. We can still see something that's basically going along the diagonal. So it's basically sending these things here. It just sometimes we have more points going to certain regions along here and less going to others as you're wrapping around here. So any questions about that? So we still get the circle very nicely. They then took a look at one where, let's take a look at this thing right here, where we can now go ahead and take a look at the persistence here. There's actually 2 points. There's 2 co-cycles. And because with 2 cycles, well, with 2 circles, how many co-cycles would you expect? You'd expect 2 co-cycles. You'd expect one corresponding to here and one corresponding to here. And depending upon which co-cycle you take, I might take the co-cycle that will map this thing nicely to S1, or I might take the one that maps this one nicely to S1, but it might be constant among. It doesn't have to be constant, but if you choose a nice representative that will pick up these circles, the nice representative will send all of these points to the constant, and then will move nicely around this circle, or it will move nicely around the other circle and move to these things here. Well, what does this thing show here? Well, in reality, if you were to do this on real data sets, you would not have the map. I mean, they had the original map because in order to create this data set, they went from S1 into R2. So they created this map here, and then they added some noise to the data. So they were able to create these maps that sent our circle here with noise into S1. And so when we went back and took a look at these maps here, that was because because they created the map by sending S1, in this case, into R3, and then adding noise. Since they had that, they were able to say that we could then go ahead and talk about how these things correlated with our S1. Generally speaking, we don't have that, but what we can do is take a look at, we have 2 maps. We have 2 maps here. One map that sends, say, by theta 1 sends this first circle onto here, and all of these go to some constant point. And then the second map that sends this circle onto here via theta 2, and then we can see how theta 1 compares with theta 2. And you can see if they are disjoint, well, basically if they're disjoint, as theta 1 maps around this, these points here are all going to be constant. So as theta 1 maps around, we're going to all be constant. But as theta 1 is constant, theta 2 will map around. So if I do a scatter plot of theta 2 versus theta 1, then we can see theta 2 versus theta 1. We have the constant maps here, that as we travel around here, we're constant. As we travel around theta 1, we're constant. As we're constant with respect to theta 1, we travel around theta 2. Questions about this scatter plot? If we then merge the two circles here, you can see we can also do a theta 1 versus a theta 2. But you can see that as we're traveling around here, we do travel, say, if we're doing this theta 1 business here, which one is theta 1 and which one is theta 2, who knows which one you come up with or which direction we're going in. But in here, we would be going around here, so we'd be going someplace. Maybe we start here and we go around here. We start here, so maybe we'll start here and go around. Over here, it's all constant. But then we have this intersection where they start, agreeing a bit. And then we go around here where this thing is now changing here, but this is constant. And so when we do our theta 1 versus theta 2, they do agree at some point. So at some point, there is some movement within here. But in many of these things, it is actually, pretty constant as we're going here. Versus when I take a look at this, it's pretty constant. There is some movement, and then pretty constant. So you can see how the two maps, theta 1 versus theta 2, correlate. Any questions about that? Another interesting example is to see how theta 1, how we can now go into, if we now take our torus. So if we now have a torus, we map that into R3 and then add some noise. Can we now come up with maps? So we will now come up with a map here. These are two different maps. We now have theta 1 into S1 and theta 2 into S1 equaling to our circle. So these are the exact same data sets, but because we've got the torus, there's two possibilities. We can either wrap around, so we can either wrap around the circle, getting a longitude, or we can wrap around a meridian. In this case, we're wrapping around a meridian. If you look closely, we're going, purple, red, blue, green, we're going around the circle in the meridional direction. And we can take a look at the correlation maps here. In this case, we're taking a look at the first thing where if we take a look at how our meridian or how our longitude gets mapped in, you can see that we have a nice correlation here. If we take a look at how our meridian gets mapped in, you can see we have a nice correlation. It just goes in the opposite direction. So we also have, in this case, we're just mapping in the opposite direction instead. But we still have a nice correspondence, so excellent correlation with the circle. But if we see how, if we take a look at theta 1 versus theta 2, or our meridian 1 versus meridian 2 in terms of, these maps, they're not going to correlate very well. We can see that the coloring, if I clear this thing up, our coloring does not correlate very well between these two maps. And so as you would expect, these things are not going to correlate very well in terms of either our inferred 1 versus inferred 2, inferred 1 versus our original known map for our meridian into S1, in terms of our original into our longitude. So, so not a good correlation in terms of, you can see that this coloring does not correlate very well with this coloring. But it does correlate very well with, in one case, getting the longitude, and in the other case, getting minus the meridian. Any questions about that? Well, one question you might have is, why aren't I getting the meridian plus the longitude? I could be getting something where, in terms of, my data, maybe I should be coloring something that, instead of going just around a nice longitude, maybe it wraps around the meridian a few times before I get to the longitude. But I'm getting these very, very nice curves. You don't actually always get that. In this case, this is the double torus, and you can see that the sort of thing that I would like to have gotten is this longitude, this meridian, and this meridian. We're not getting that in this case. Otherwise, we would be getting some constants. You can do a change of basis and get things that are a little bit more constant in some of these things, so that we can see we're going around the meridian here. We're going around a longitude here, meridian here, longitude here. So with a change of basis, you can get a nicer basis. But in many cases, you get a pretty good basis. And the way to get the pretty good basis is, remember in our theorem, we said, well, given alpha bar, alpha, and f, we can create this theta. Well, given alpha and f, I can take the naught of f and add it to alpha and get my alpha bar. And so in reality, what we want to do is, our givens are instead going to be actually, I think I have this reversed. I think this should be z and this should be r. I'll need to double check that. But given alpha and f, we can then create our alpha bar. Yes, so this should definitely be r, and this should have been z. Sorry about that. If I add something whose codomain is real numbers to something whose codomain is the integers, well, a real number plus an integer is a real number. So this one should have been the integers, and this one should have been r. But if I have this cocycle and I have this f here, well then, since this is a cocycle and this is a cocycle, remember if I do d1 composed with d naught, I get 0, and so this sum will be a cocycle, so I'm guaranteed a cocycle, then I can create this theta. So I really just need to find alpha and f. Well, the actual algorithm is to go ahead and find this one where this thing will actually, C1 of x comma z will be a subset of this thing right here. But given an alpha, whether it be in here or here, there's going to be a unique thing that minimizes the length of our cocycle. And so it will minimize the length of our cocycle given, we're basically taking a look at, given a cocycle, let's look at all the other cocycles that are in the cohomology class of alpha. So we're basically looking at the cohomology class of alpha and saying, let's take a look at the nicest one. Let's take a look at the nicest one. And the method to do that, well, there is a bit of a problem in that we want this one with integer coefficients, but just like for the barcodes for homology, the barcodes for homology are not unique, and they are not easily to calculate over the integers because it's a ring and we don't have inverses. So instead, Dionysus will do it over Z mod P, determine the persistent homology, lift it to a 1 cocycle, lift this 1 cocycle in here to a nice 1 cocycle in here, where we won't have time to go over those details because we're already over time. Then simplify the cocycle via that least squares minimization, and then use that to create the map right here. And all of that can be done in Dionysies. Just look at this one right here, click on that, and you can read through to see how that goes too. So I'm afraid we only got through the cohomology. We will briefly discuss stability after the conference. The majority of what we will discuss is biological applications. So we will focus on looking at what real data looks like for DNA, RNA, and proteins. And if you have particular applications or particular things that you want to see in analyzing data, send me an email and I will see if I can work that into our November and December lectures. Any questions on any of this stuff? Okay, so I will either see you at the IMA workshop or in about a week. Feel free to email me any questions in the meantime, and I will email you some recommended videos this Sunday. This